Hi there! Today we will be seeing the Briggs-Rauser reaction. That is one of those reactions which make people of all age reflect on how cool science exactly is. The reaction basically begins with the mixing of three colorless solutions. The resulting mixture formed then oscillates periodically in color from clear to amber to dark blue, then back to clear, amber, and so on. It is a riveting scene, and the chemistry behind it is even more fabulous. Now, let's see the most interesting aspects of this chemical reaction, also known as the oscillating clock. First one is one of a small number of known oscillating chemical reactions that are the most fascinating of all the chemical reactions. To many, these reactions are engaging examples of chemical magic, so they are a mystery and a challenge. Perhaps what makes oscillating reactions so fascinating to chemists is that they seem to contradict common sense. So, how you can contradict a common sense with a scientific experiment, you may asking? Well, experience tells us that under a given set of conditions, chemical reactions go in only one direction. So, we rarely find a chemical reaction that appears to reverse itself, much less to do it so repeatedly. But what is cool in this chemical reaction is that they act like a pendulum. A pendulum oscillates from side to side through its equilibrium position, and this oscillation can be attributed to the interconversion between potential and kinetic energy, therefore the mechanical energy. So, analogous to this physical process, this chemical oscillator may seem to swing through its equilibrium composition. However, this is contrary to the second law of thermodynamics, which states that once a chemical system reaches equilibrium, it cannot deviate from that condition spontaneously. Therefore, oscillations in chemical reactions cannot be like oscillation of a pendulum because they don't have mechanical energy. So, what makes this experiment and this chemical reaction so interesting is that we are literally breaking the rules of thermodynamics. Cool, right? The second fact of this reaction is that there is a quantitative evidence that when the chemical reaction is taking place, there is a varying voltage potential. So, when the voltage is measured across the experiment, it has been seen that the mixture oscillates. The third fact of the Briggs-Rauser reaction is that there is a distinct visual confirmation of it. When the different chemicals are mixed in the solution, starting colorless, the result is an impressive display of cyclic color changes from clear to yellow to dark blue. Explanation. The three solutions initially mixed together contain a source of iodate, a strong acid, malonic acid, a manganese cation, hydrogen peroxide, and a starch indicator. What ultimately happens during this oscillating chemical reaction is that the iodate, malonic and hydrogen peroxide, and the strong acid react in a stepwise manner, ensuring a series of interdependent reactions. Some of these reactions contribute to the color change that are seen during the process. The two-component reaction can be said to occur upon the initial mixing, triggering of the reaction. One of them does not actually result in the direct production of colored species. It merely involves the production of the all-important colorless epoidous acid from iodide and hydrogen peroxide. The epoidous acid then contributes to the format of iodine and eventually accumulation of iodide. These two accounts for the amber and blue colors respectively. At this point, you might think that this is becoming too complicated, but please bear with me for a little longer. This is where it becomes really interesting. As the reaction starts, a lot of iodous acid gives out iodide in the presence of hydrogen peroxide. Then, the acid acts with the iodide, it helping producing the form of iodine, resulting in the sudden amber color that is seen. However, iodide, which is less and less acted upon by disappearing acid, becomes more prominent in the mixture, and this offsets the color of the latter to dark blue, as it interacts with the iodine and the starch indicator. Eventually, iodine is eaten up by the malonic acid and its removal turns the solution to colorless once again. From the onwards, it is the same cycle over and over.